Hello dear students, welcome to the channel Pen and Paper Chemistry on YouTube. Continuing with our topic on electrochemistry, the next heading that we are taking up now is factors affecting electrode potential. We need to remember over here that whenever we are going to talk about electrode potential, we are talking in terms of reduction potential. As in the earlier video I had told that the general rule is that we talk about reduction reaction and we talk about the reduction potential as the standard value when you are talking about electrode potential. So if I write any generic reaction as Mn positive in an aqueous solution plus n electrons in equilibrium with the metal or the element changing into the elemental state, this is how I will write an equilibrium reaction. Now looking at this equilibrium reaction itself, you would be able to give me a lot of factors which will affect the electrode potential. First and foremost that comes to the mind is concentration. Yes, because if you see we are involving ions over here. So if the concentration of the ions will change, so will this equilibrium. If you can recall the chapter on chemical equilibrium, you will be able to relate to this, right? So the concentration of ions in any electrode will affect its electrode potential, and not just for the electrode, it will affect the EMF of the cell as well. For example, if you see Zn plus Cu2 positive giving you Cu plus Zn2 positive. Now we have all the while been talking about this galvanic cell. Now this galvanic cell is involving zinc ions and copper ions. So the concentration, a change in the concentration of any of these ions will affect the equilibrium and the EMF of the cell. How does it affect is what we are going to do in depth in today's lesson under what we call as the Nernst equation. A little more of that later. Let us see the other factors also which affect the electrode potential. Of course, nature is the first thing that affects. You know that the standard reduction potential of zinc is negative 0.76 volts, whereas the same value for copper is 0.34 volt. And in our last lesson, we have listed the electrode potential of a number of electrodes, and we found that no two electrodes have the same electrode potential. Third is the temperature. Again, going back to what we do under the heading chemical equilibrium, we know that this is a process which is involving energy change. That means either heat will be liberated or absorbed. Usually heat change will be involved. Now where there is heat change involved, there will be temperature, which will be one of the factors to affect any equilibrium process. Pressure. Yes, it does affect the electrode potential. A very simple example, if you recall, we've spoken about She, that is the standard hydrogen electrode, right? Or also called as NHE, normal hydrogen electrode. There we mentioned that we are introducing hydrogen gas into this glass tube, and we were specific in saying that we are introducing the gas at a pressure of 1 atmosphere. There are other electrodes as well where gaseous substances are involved. So pressure is another factor which affects the electrode potential as well as the EMF of a cell involving gaseous substances. So now let us move on to the most important factor over here, concentration. Why I am saying most important? It's important from your learning point of view, because we are talking about the change in the concentration of the ions. We will not be talking at this stage about a lot of gases involved in the electrode reactions. For now, we will limit ourselves to concentration, and that requires a slight in-depth study, that is the Nernst equation. Now, before I go on to Nernst equation, my request that I make every time, please get a pen and notebook ready so you can note down, you can write as well as understand what I am going to explain now under Nernst equation, because they will become your handy notes for reference in the future. So you won't have to look elsewhere for written notes and come to this channel for videos. You will have ready reference, and when you write something with your own hand, it gets embedded also into your mind. So get going, get a pen and paper ready. I'm waiting for you. I'm so impressed that you have actually got the pen and paper with you and you're ready for the next part of this lesson. And that is the effect of concentration on electrode potential or the EMF of a cell. We know that EMF of a cell definitely depends upon the electrode potential. So what I'll do is I'll build on what we already know to zero down onto something which is new for you. You have done equilibrium reaction, and we are representing a simple galvanic cell as an equilibrium reaction over here. Zinc solid plus Cu2 positive aqueous in equilibrium with zinc ions in an aqueous solution plus copper solid. Now we've already done under the topic of thermodynamics the relation between the Gibbs energy and the equilibrium constant, and here it is the reaction quotient to be specific. Delta G, that is Gibbs energy, is a measure of the useful work obtainable from a system. And here the useful work that is being obtained from the system is in the form of electrical energy, which is represented by NFE. Now we had derived this expression under the topic of Faraday's laws. Yes, we have already covered this topic on this channel. So we have derived a relation between delta G and the EMF of a cell already. So what I'm going to do is I'm going to take some bits and pieces from thermodynamics and some from the Faraday law. So if you notice over here, I can replace the delta G by negative NFE, because here it is minus delta G is NFE. So we have the expression minus NFE. N stands for the number of electrons which are involved in that change. F stands for Faraday constant, 96500 coulombs. E stands for the EMF of a cell. If you notice, we have another variation of delta G with a small zero on top. This stands for the standard value of a substance. Standard value means when you are taking the substances in their standard state under standard conditions of temperature, right? So here we have specifically written, so when you are showing a derivation, it is always good to write the equation and also explain the meaning of the symbols that you are using in your derivation. That brings clarity to your work as well as your thinking. So delta G naught that we have here is standard change in Gibbs energy. Delta G is change in Gibbs energy. Here I have not included the word standard because here the conditions are different than the standard conditions. Any other condition other than the standard condition. R is the universal gas constant. There are three different values. The values that we are going to use here is 8.314 joule per mole per Kelvin. What makes me take this value is We are talking about energy over here. So we will take the value of R also in similar units corresponding to energy, which is 8.314 joule per mole per Kelvin. Temperature, absolute temperature, that is the temperature in Kelvin, which is denoted by capital T. If it was a small t, then it would have meant that we are talking about temperature in degrees Celsius. Q is the reaction quotient. What is reaction quotient? It is the ratio of the product, of the concentration of the products raised to their coefficient divided by those of the reactants raised to their coefficient. For example, in this equation that I have taken, here the products are zinc ions. Yes, I will take the zinc ion. There is no coefficient over here. There is no 2 or 3 over here. So I don't put any power over here. Then there is copper. Now if you notice, copper is a solid over here. The concentration of the solid substances is taken as unity throughout the course of the equilibrium reaction. So we will not take this into consideration, right? Come to the reactants. Here I have zinc solid. So what concentration? How do I represent concentration for zinc solid? Yes, square bracket zinc. But again, because this is in the solid form, we take it as unity because the reaction is taking place only on the surface. So what do I write for the reactants? Yes, only the copper ions if there was a coefficient over here. So let's suppose I had zinc plus 2 Ag positive giving me, or in equilibrium with zinc ions plus 2 Ag. That then, yes, perfect. Then in that case for the reactants we would have written for the products is zinc ions, and for the reactant it would have been the silver ion raised to the power of 2 corresponding to the coefficient that we have over here. I hope this makes it clear. Reaction quotient means it's the equilibrium constant when the equilibrium has not been reached. That means it is the equilibrium constant of a reaction for a concentration other than the concentrations at equilibrium. Coming to our derivation once again, we have minus NFE equals minus NFE naught plus RT natural log of Q. Natural log means to the base E. Till now in your study you would have been dealing with logarithms to the base 10, right? But this is to the base E. If you are not confident about logarithms, about how to use them to solve your numericals, there are 2 videos on this channel where I have thoroughly and exhaustively dealt with logarithms. For those of you who are allowed to use calculator, of course, that's a blessing. But for those of you who have to use the logarithmic tables, don't worry, that blessing comes to you in the form of this channel, because I have loaded and I have clearly taught you logarithms in that particular video. So coming to natural log of Q. Now what do I do is, I want an expression as to how E gets affected by Q. So I divide the whole equation, or we say the whole expression from the left hand side, we divide it by minus NF. So this also by minus NF, this also by minus NF. So what we have over here, sorry, there should be a minus over here, right? So this minus minus becomes plus, minus minus becomes plus, and what do I have left over here is E is equals to E naught minus RT upon NF natural log of Q. It's not easy to deal with natural log, so we need to convert it to the base 10. That is that logarithm to the base 10. So E is equals to E naught minus RT upon NF into 2.303 log of A. Those who don't want to get into the nitty-gritties of natural log and to the base 10, I know there are a lot of students who don't do maths at higher level. Don't worry. Simple, natural log to convert it to base 10, you multiply it by 2.303. I think for you at this level, good enough. Don't worry. 2.303 log of Q. Now, next thing that we need to do is, to get a simplified expression, I need to put the values of the constants that I can write. So, R 8.314, 298 Kelvin, 96500 coulombs is the value of F. N means the number of electrons which are involved in the chain, in the equilibrium reaction. So in both the reactions that I have taken, the electrons involved are 2. So here it will be 2, although I am not putting 2 because we want to derive a generalized expression. So when we put the values of all the constants, F is 96500, we get E is equals to E naught minus, yes, you can check the calculations, 0.0591 upon N log of Q, where Q is the reaction quotient, ratio of the concentration of the ions of the products and reactants at any point other than the equilibrium. So what will happen at equilibrium? At equilibrium, this Q becomes equal to Kc, that is the equilibrium constant of this particular reaction. So we have the final expression as E is equals to E naught minus 0.0591 upon N log of Kc. This expression will provide us a lot of detail, right? So let us see how this particular expression is useful for us. Before you go ahead, just go through this derivation so that there should be no doubts lurking in your mind when we go on to the next step. Coming back to our expression, E is equals to E0 minus 0.0591 upon N log of Kc. Now Kc means that we are talking about the concentration of products divided by the concentration of reactants. What if I reverse it? I take the reciprocal. So what I have got over here is E is equals to E naught plus, because we are reversing, reactants come in the numerator, products go in the denominator, the sign changes, plus 0.0591 upon N log of the concentration of reactants divided by the concentration of products. Now let me relate to the example that we have been taking all this while. Zinc plus copper ions gives us zinc ions plus copper. So my reactant over here is Cu2 positive and product over here is zinc ions. Here, if you decrease, arrow down, my arrow down means here decreases. So if the concentration of zinc ions decreases, that means the numerator is decreasing, and the concentration of copper ions here increases, right? So what will happen is E0 plus some value, it will be a positive value, right? So if it's a positive value, means the new EMF of the cell will be more than the standard EMF of that particular galvanic cell, right? So if you notice over here, the EMF of a cell does depend upon the concentration of the solution that has been taken in order to set up the redox reaction. Now you will say that here we are talking about the full cell reaction. What about the electrode, a single electrode? So let us study that as well. Now I will, as I said, I will move from complex to easy, right? So let me take a single electrode, and as a rule we will take the reduction reaction. Mn positive plus n electrons gives us M solid. This is a generalized reaction. So I will have E is equals to E naught. Either you can start from the base equation. 0.0591 upon n log of Kc, that is the concentration of products divided by the concentration of reactants. Again, because this is a solid, concentration is taken as unity, that is 1. Also remember square brackets specifically. Square brackets means you are talking about concentration in moles per liter. I can flip them, so Mn positive. So the sign here becomes positive. Now again correlate the same way. If the concentration of Mn positive increases, there will be an overall increase in the EMF of the cell. Increase means there will be more tendency for this reaction to take place. That means this ion now wants to gain electrons and turn into a metal. When it has a tendency to gain electrons, gain of electrons is correct. It's reduction, rig, oil rig. Reduction is gain of electrons. And reduction means it's the perfect, it's the cathode. In other words, supposing now I take the same combination. So I have copper in a solution of copper sulfate and another copper in a solution of copper sulfate. But in one I take the concentration as 0.01 molar, in the other I take the concentration as 0.001 molar. Both are copper sulfate. Copper sulfate solution, copper sulfate solution. Here I have copper electrode, I have copper electrode. What is varying in the two of them is just the concentration of the copper ions. What if I connect the two of them? Do you think there will be current flowing in between them? Yes, there will be current. And these type of cells are known as concentration cells. So concentration cells use the logic that the EMF of the cell depends upon the concentration of the ions. So the one which is having greater concentration of the ions will behave as the cathode. The one with the lower concentration will behave as the anode. But this will work only till the concentrations become equal. Once the concentrations become equal, then the cell reaction stops. For all this, we have to thank Nernst, a German physicist and chemist, who gave us this equation, which is known as the Nernst equation, a very important equation in electrochemistry, which leads us to a number of things. One, of course, we can determine the electrode potential. Second, if you notice, we are using the concept of equilibrium constant over here. So what is happening is, with the help of this equation, I can also determine the equilibrium constant of a reaction. How? You carry out a reaction such that the equilibrium is achieved. Once the equilibrium is achieved, your E is the same as E naught, right? So that helps us to determine the value of Kc, that is the equilibrium constant. Same way, it can also be used to determine the feasibility of a particular process. We shall be going into that detail as well. This particular expression also helps us to determine the solubility product of a particular sparingly soluble salt. We shall now be taking up numericals based on this concept in order to clear your doubts and to give you confidence in attempting numericals on this topic. So take a break, have a glass of water, pause the video and then come back to do the numericals with me. Are you ready to do some numericals? Let's start with the first one. The following reaction takes place in a cell. aluminium solid plus 3 Ag positive, and this is the concentration which is mentioned. Al3 positive, again the concentration of the aluminium ions is given to you, plus 2 Ag, which is in the form of a solid. You have to identify cathode, anode, calculate the standard EMF of this cell, calculate the EMF of this cell. Please understand the difference. There's a not sign over here, there's no not sign over here. When the data provided to you is E naught Al3 positive, Al is negative 1.66 volts, and E naught Ag positive, Ag is 0.80 volt. Okay, let's start with the first thing. Would you like to try and answer the first and the second and maybe the third part, because we've already covered this in the previous video on electrode potentials and EMF of a cell. Go ahead, give it a try. You can pause the video, give it a try, and then tally your answers. Al changing to Al3 positive, loss of electrons, right? So loss of electrons is the anode, right? Cathode, Ag positive changing to Ag, gain of electrons. Gain of electrons is reduction, and reduction is taking place in silver, right? So this is one aspect. If you have answered these two questions correctly, very good, half mark here. E naught cell, how do you determine EMF of the cell? Standard EMF of the cell. Simple, EMF of the cathode, electrode potential of the cathode minus the electrode potential of the anode. Now, very careful over here. Sometimes questions involving the calculation of the standard EMF of the cell are very easy. The trick is in these values. If you notice over here, I have provided you the reduction potential, the standard reduction potential of aluminium and standard reduction potential of silver. Many a times, just to be naughty, we teachers, you know what we do? We'll just put it over here as Al3 positive, and this is plus. What have I done over here? Yes, I have expressed this as oxidation, and the potential provided to me over here then becomes oxidation potential. Whereas in this formula, we have to just put the reduction potentials of the electrodes, right? So please be very careful. This can be a 1 mark or a 2 mark question, but then don't be disheartened if you find that you have calculated E naught cell but your answer does not tally. These are reduction potential. So we have to apply the reduction potential over here. And thankfully in this question, the values provided are the reduction potential. So cathode is silver, anode is minus 1.66, and give me the value. Yes, it is 2.46 volts. Am I right? Anything? Yes. Go on to the fourth part of the cell. That is the EMF of this cell. Now this is where the Nernst equation comes in. Right? We have done the Nernst equation, so we will have E is equals to E naught minus 0.0591 upon N log of concentration of products. Now in the products I have Al3 positive, there is no coefficient to it. What about silver, Ag? Do I put this value? No, because it's a solid, so the value is 1 divided by the concentration of the reactants raised to the power of their coefficient, right? So we will have over here Ag positive whole thing to the power 3. Now here I would like to insist that while calculating E naught cell, we did not take the coefficients into consideration because it's an intrinsic property, right? Whereas EMF of the cell, not under standard conditions, but EMF of a cell depends upon the concentration. So that is why we have to take the coefficient into consideration. Now let me try and explain to you as to how we are going to calculate it. If you want to calculate it yourself, please go ahead, give it a try. You will feel happy about it. Okay. We got the EMF of the cell and I will need it. So let me leave it here on the board. So E is equals to E naught, which is 2.46 minus 0.0591 upon how many electrons are involved over here? Aluminium is losing 3 electrons, silver is gaining 3 electrons. Each silver ion is gaining 1 electron. There are 3 silver ions involved in this equilibrium reaction. So divided by 3 log of concentration of aluminium moles per liter 0.120. Concentration of silver ions 0.001, whole thing to the power of 3. Right? Now what you are going to do is you will now divide and apply the log values. So this comes out as 2.46 minus 0.0197. Have I got it right? Correct. Now log of, how do we do this? Log of 0.120 minus 3 log 0.001. If you are not clear about this concept, I request you to visit the video on logarithms, thoroughly explained completely in detail. I am very confident that after watching that video you will not say that I don't know logarithms or I am scared of doing numericals which involve logarithms. It's so easy, right? Now I'll explain to you how we do the calculations over here. 0.120. So I will put the characteristic and see the logarithmic tables. 12 under 0 gives me 0.0792. 3 into log of 0.001. So this is simply 3 bar. So there is only characteristic 3 bar gives me 3 times 3 is 9 bar. So minus 9 bar. Again, if you are not able to relate to it, please see the video on logarithms. And we get over here 2970. Now this is minus 1 minus 9 gives me a value of 8. Right? So can we now put the values and multiply and get the answer? Go ahead. 2.46 minus 0.0197 into, you will get over here 8.0792. When you calculate this, the final answer comes to 2.300 volts. If you've been able to get it, very good. Feel happy about it. Yes, you moved a step ahead. If you have not been able to get it, don't worry. Go back. Go back step by step. See where you went wrong. See where there could be, sometimes just this small error where you've not taken this 3 into consideration, or there may be that you've got stuck at this point. That does not mean that your full answer or your full concept is wrong. If I tell you from the examination point of view, because you have done till the second last step, you still stand to gain some marks in this particular question. So please don't give up. Just by looking at the question, it's like, oh my god, I don't know what these values are. Don't worry. Move step by step by step and you will get the solution. Or if you don't get the correct answer, at least you would have moved a step closer towards it, right? So don't give up. Don't give up the baby steps. You taking baby steps only will lead you to your destination. Would you like to do one more numerical based on this? Or would you like to try some numericals yourself and clear your doubts here? Okay, challenge 10 numericals. Let me see if you are able to do 10 numericals on this concept before I post the next video. 10 numericals based on Nernst equation, EMF of the cell reaction, and maybe some numericals where you have to calculate equilibrium constant. So go ahead and give it a try. If you are not sure, most welcome to clear your doubts through the comment section. Happy studying to all of you. Take care of your health. Do subscribe for more videos in chemistry and don't forget to share the channel with friends and classmates. See you in the next video.